My name is Jeff Franklin. I am the original architect of the commercial software package called Azore. If you're interested in finding out more about Azore, you can find it at this website. If you're interested in contacting me, I have two paths here, one through LinkedIn and the other one through my email address. Today, this discussion, I'd like to talk about a two-dimensional hill benchmark. This is a benchmark that I used decades ago in the original development of Azore, and today we're going to revisit that and look at some aspects of that benchmark. So let's get started. So the benchmark basically is a two-dimensional case, and it has basically a hill, which is just kind of a bump, and it's in a slot, basically. And the slot in the experimental setup was 170 millimeters high, this Y height. And the hill itself was about 28 millimeters high. The working fluid was water, and the viscosity used in this benchmark was basically 1 e to the minus 3, and a density of around 1,000. If you're interested in finding out more about this benchmark, you can find it here at this reference point, right here, this reference. So, and it has basically a nominal velocity that is going from left to right here of about 2 meters per second. So that's kind of the way this experiment was set up. So in terms of the data that's available from the experimental setup, there are a number of traversals made. So these red lines here throughout the domain are where experimental data was collected. So there's one line right here kind of significantly upstream of the hill itself, and then a number of lines going downstream as the flow goes over the hill, and then there's a kind of a recirculation zone that forms here, and then as it recovers. So these are the experimental data that are available here, and that experimental data is basically of the nominal velocity field traveling in the left-right direction. So that's the data that we're going to really look at and compare our predictions to. So maybe I'll start by just kind of looking at what the nominal velocity field kind of will look like in this particular case. So we have kind of a parabolic, fully developed velocity profile that is approaching the hill. And then as it goes over the hill, the flow accelerates. So we're kind of looking at total velocity right now. You can see by the colors that the velocity is increasing. There is a low velocity recirculation zone here. You can tell by the velocity vectors that indicate kind of the directionality of the fluid in this area. So we have the flow accelerates, goes over the hill, then it begins recovering and reattaching down here, and a recirculation zone is formed. And these red lines again are where the experimental data is taken that we can use to kind of compare our CFD predictions to the experimental data. So for this problem and the discussion isn't about how you can get like the perfect answer here. What we're really going to do is we're going to kind of exercise. We're going to pick one mesh topology, and we're going to look at what kind of variation we might get if we use different methods. And here we're going to look at solving this problem using Azore, the software package I developed, and we're going to look at it using the K epsilon turbulence model and the K omega SST turbulence model. We're also going to look at the predictions for the same case and same setup using Fluent, also using the K epsilon turbulence model provided by that software package along with the K omega SST turbulence model. So that's kind of the objective. That's kind of what we really want to look at here. So Here we'll first start by talking about the domain, the overall domain that we're going to use here. So we're going to start with a uniform velocity over on the left-hand side of this space, and we're going to kind of predict the development of the fully developed flow. Right here is kind of an overall view of the mesh density and the mesh topology that was used. And then if we kind of zoom in right here, this is a kind of a zoomed in view of the mesh topology around the hill. So that's a kind of an overview of the mesh topology that we're going to use as we kind of exercise these different turbulence models and these different software packages. So before we go kind of dive into looking at the results, let's just take a few minutes and look at the mesh topologies that were selected here. So on the left-hand side, you can see right here, this comment over here, we have basically boundary layer cells that are often called, and we have high aspect ratio cells, and those are kind of appropriate in this area because the flow it's mostly two-dimensional or one-dimensional right here. It's kind of developing as it goes along here. And so a high aspect ratio cell makes sense because the flow is really kind of one-dimensional here and here. But you'll notice that right down in this area, the aspect ratio of the boundary layer cells become very squarish. And that's because the variation of the boundary is changing, as well as the flow structures in this area, as the kind of one-dimensional flow is kind of distorting and becoming two-dimensional flow. So we want to kind of reduce the aspect ratio of our boundary layer cells to perhaps a little bit less than 3 to kind of capture that properly. You'll also notice here that the flow structure in this area where our steep gradients are going to be, we maybe have a little bit denser mesh to capture some of those flow structures. So that's just a few comments about the mesh length scales and topology that's being used for this benchmark study. So here is the first row of data, and we're kind of looking at the experimental data right here along this line, and we also have the predictions. So the black line with the little round circles are the experimental data. They're kind of connected together, and each one of the round circles represents where data was taken for each one of the locations along here. And so this position right here, so like the distance from this point out here kind of represents the magnitude of the velocity that was measured there. And from here to here is the position from the bottom of this slot to the top of the slot as you pass up, from here to here. So, and then we have 4 simulations that were run. And so we have a solid line, which is used for the Azore predictions, and there's a red line for the K epsilon predictions and a blue line for the K omega SST predictions. The dashed lines are used to indicate the fluent predictions. The dashed red line is for the K epsilon predictions by fluent, and the blue dashed lines are the K omega SST predictions. And you can see right here that all of the predictions are very close to one another. There's not very much variation in the turbulence model used or the software package used. So now let's move on and look at some more experimental data. Here we're looking at the experimental data in this area, right as it passes over the hill. And you can kind of see the geometry of the hill put in here for reference along with the experimental data. And it kind of follows the same theme where there are multiple data sets on here. So like this line right here represents this line right here. And the distance between here and here is the experimental data. And here we kind of have a reference. So the length of this right here is 2.147 meters per second long. And that is the distance between here and here. So you can kind of see that maybe this distance and this distance, it's right around 2 meters per second. And that kind of pattern repeats. So like this line right here represents this line right here. And you'll notice that the experimental data, as it comes down, doesn't go all the way to the bottom because the hill position is right here. And so this shows the experimental data right here and the numerical predictions at each one of the locations as the fluid passes over the hill. And that goes all the way down to this position right here. And here you can see where the recirculation zone. So like you'll notice right here that these points are behind this line, kind of indicating a velocity going in the reverse direction. And you can kind of see that a little bit here as well, where these points are behind this line. And this line right here is this line right here. So it's in the recirculation zone. So that's kind of how this is set up. And so we're going to kind of move our way down this slot, and let's look at the experimental. So now we're in this area. We're between this line of experimental data and this line of experimental data. And it follows the same theme, where this line right here represents the position, and then the deflection or the distance from this line out here is the velocity position. And you can see there's a negative velocity right here where the velocity is recirculating. And then as the pressure or as the recovery of that recirculation zone progresses, you can see that that recirculation zone and the negative velocities become smaller and smaller until there's really not much negative velocity left at all. And then this is the last section. We're really out in the recovery stage right now. It's fully attached to the bottom of the slot in this area, and now the flow structure is just returning to fully developed flow downstream. And then this is the final position, significantly downstream, and it's fully attached and it's returning to kind of a fully developed flow profile. So let's just think about this a little bit. You'll notice at the beginning that the prediction of the velocity profile, and the prediction of the velocity profile didn't really match the data that well. And the original model only really had a 3-meter entrance length. And the documentation for this benchmark, they kind of suggest that maybe 1.5 meters is a sufficient distance upstream to start a simulation. But the experimental data, if you look at it closely, indicates that the top and the bottom boundary layers, they kind of have combined together. And maybe that isn't enough distance in our prediction, since we started from a uniform velocity for that boundary layer to have fully developed. And so maybe we can run this simulation again, and we'll add an extra 6 meters of entrance duct length, or that slot. We're going to increase the distance, and we're going to look at how that might change our predictions. This is kind of akin to, we really need to make sure when we're putting together a CFD model in general that we choose a good boundary condition location, because that has a pronounced impact on our ability to predict what's happening. So let's just look at that. And so what I've done here is I've taken, and we've run this in Azore, and now the red and black lines are all by Azore, but what we have done is we've taken the dotted lines, rather than referring to the fluent predictions, they now refer to the prediction with the increased distance on our entrance right here. And so if you look right up in here, so the solid line right here is our previous prediction, where we didn't really capture the boundary layer development. And now if we increased our distance, now we have given our domain the chance to actually predict that fully developed flow. And the solution looks much closer to the data. So simply changing our boundary condition has significantly improved our prediction at this location. But the question is, what happens at our other locations? So let's just kind of progress down and look at the data again. And you'll notice in this area, it's very difficult to distinguish the differences between the two predictions here. It doesn't have as much of an impact in this area. It's very difficult to distinguish. So in this area, it's not really sensitive to it. That the entrance area, it was sensitive to that choice and boundary condition, but in these, it's not as sensitive. If we go a little bit further downstream in this recovery area, then you do see just a tiny bit. If you look very closely, you'll notice that the dashed lines have a little bit more curvature, and the solid lines, which had the shorter entrance length, those are a little bit straighter, and that curved line maybe represents the curvature that we see in the experimental data. So we have made a slight improvement in the downstream area there, but it's pretty small. And like if you were doing engineering analysis on this, that may not be enough of a difference to warrant doing, adding that additional distance. It depends on what you're looking for. And now we're out at the very end in the recovery stage, and it's very difficult once again to see the differences between these predictions. And then at the very end, you can still see a little bit of how that parabolic profile does affect the prediction at the very end here. So that kind of completes the discussion that I'd like on all the material that I'd like to talk about for this benchmark. But to just summarize here, what we really saw was that the variation between the two software packages, ANSYS Fluent and Azore, was kind of minimal. Really couldn't tell the differences between the predictions. Actually, the prediction between the two turbulence models is minimal as well. You've pretty much got the same answer. But really the two things that are kind of interesting about this are the differences in the predictions between selecting the appropriate boundary condition type. And that's one thing to really keep in mind when you're putting together your CFD models. When possible, we want to really include some significant geometry feature upstream of any area of importance. Note here that extending the domain did not really significantly improve the predictions after the hill feature, only before. And also one of the things that we should always keep in mind is if we really intend to have fully developed flow assumptions, we need at least 30 hydraulic diameters to become fully developed. So this is one benchmark of many complex benchmarks that were used in order to develop and ensure that Azore gives you really high quality solutions. If you're interested in more content like that, please visit our website at azorecfd.com, or if you want more YouTube videos, we have a lot of them and you can find them here at azorecfd.com.